Take a look at the shirt you're wearing right now. What's actually holding it together? It's not just the thread, you know. It's an entire invisible world of molecular architecture. We're going to zoom all the way in, way past the fabric, past the individual threads, down to the tiny fundamental rules that give our clothes their strength.
Seriously, think about it for a second. A cotton shirt is comfortable, sure, but a nylon rope can literally pull a car. The difference there isn't just the material itself, it's a hidden design. The answer lies at a scale our eyes can't even begin to see, in the secret rules that dictate how every single fiber is put together.
So what actually makes a fiber? Well, a fiber. Turns out it's not random. There's a fundamental blueprint, a set of rules that a material absolutely has to follow at the molecular level to even earn that title.
And you know what? The blueprint is actually pretty straightforward. First, you need these long, straight chain molecules. Just picture tiny strands of uncooked spaghetti. Second, you got to get those strands to line up parallel to each other. Third, they need to have some kind of natural attraction, a way to stick together. And finally, they need just a little bit of wiggle room, some freedom of movement so they have a bit of stretch. You get those 4 things right, and boom, you've officially created a fiber.
Okay, so we've got the blueprint, but here's the catch. All of this is happening on a scale that's thousands of times smaller than a single human hair. So how in the world do scientists actually see if these rules are being followed? Well, as you might guess, they have a pretty specialized toolkit for the job.
Right? It's one thing to have a theory about how things should be arranged, but how do you actually prove it? How do you get a snapshot of these tiny molecular lineups? Well, you don't use a regular camera, that's for sure. You have to get clever and use physics.
Scientists have this whole array of tools to peek inside a fiber structure. And while all of these are important, we're going to focus on 2 of the real heavy hitters, X-ray diffraction and infrared absorption. Why? Because together, they reveal a fiber's most important secrets.
Think of these 2 methods as 2 totally different ways of asking a fiber questions about itself. One method is kind of like an interrogation. It demands to know all about the fiber structure. The other is more like listening, gently asking what it's made of.
First up, the interrogation. This is where scientists basically shoot a beam of X-rays at a fiber to force it to reveal its internal layout. It's called X-ray diffraction, and it's all about finding order in the chaos.
So here's what happens. The X-rays hit the fiber. Now, in the parts where the molecules are arranged in these really neat, orderly layers, what scientists call crystalline regions, the X-rays bounce off in a super predictable pattern. It's kind of like skipping a stone on a perfectly smooth lake. But the messy, jumbled parts of the fiber, the X-rays just scatter all over the place. No clean reflection there.
Now, this reflection pattern isn't random at all. It's governed by this really elegant little equation called Bragg's law. Now, don't worry, we're not going to do a math quiz. But what is really important is that little d in the formula. By measuring the angle of that perfect reflection, scientists can calculate d, which is the precise distance between the atomic layers. This gives them a hard number for just how orderly and crystalline that fiber really is.
Okay, so that was the interrogation, which tells us all about structure. Now it's time for the listening part, which tells us about composition. Instead of bouncing rays off the fiber, this time scientists pass infrared light through it, and they listen very carefully to what gets absorbed.
When they do this, certain chemical bonds inside the fiber just get excited. They soak up the energy from the infrared light and start to vibrate like tiny tuning forks. On a chart like this one for nylon, all those vibrations show up as peaks. Each peak is like a musical note being sung by a specific part of the molecule.
Let's decode a couple of these notes, shall we? You see that big peak at 1640? That's the sound of carbon-oxygen double bonds stretching out. The peaks around 2900, that's the vibration of the CH2 groups, and that one way up at 3305, that's the NH bond singing its tune. Every single peak is a unique chemical fingerprint, telling scientists exactly what ingredients are in that fiber.
So let's just put it all together. The infrared method listens to all the molecules, the messy ones and the neat ones, to identify the chemical ingredients. The X-ray method, on the other hand, is pickier. It only looks at the orderly crystalline parts to figure out the physical structure. So to put it simply, infrared tells you what it is, and X-rays tell you how it's built.
Okay, so we can see the blueprint and we have the tools to measure it, but why does any of this matter? Well, it matters because this invisible microscopic structure is what directly creates the real-world properties that we can actually see and feel.
Let's start with a big one, tensile strength. In other words, how much can you pull on a fiber before it finally gives up and snaps?
So what determines that strength? Well, it comes down to 2 key things we can now measure: the more crystalline a fiber is, and the more oriented its molecules are, meaning the more they line up perfectly parallel, the stronger it gets. That neat, orderly structure spreads any pulling force evenly across all the molecules, making the whole fiber incredibly tough.
But hey, there's always a trade-off, right? Let's look at another property, extensibility. You know, how much a fiber can stretch.
And this is the great trade-off of fiber science. The very same things that make a fiber super strong, that high crystallinity and perfect orientation, also make it less stretchy. A perfectly ordered structure is strong, but it's also kind of brittle. A messier, less ordered one is weaker, for sure, but it's also way more flexible. You can have strength or you can have stretch, but it's really, really hard to have a lot of both.
So after all this science, after looking at X-rays and infrared charts and everything else, what's the one thing you really need to remember? This is the whole ballgame. The reason a wool sweater is stretchy and warm and a nylon rope is brutally strong but doesn't stretch much, it all comes down to the molecular blueprint we just explored. The hidden world of atoms and bonds is what creates the world of textiles we live in every single day.
And that leaves us with a really powerful idea. For almost all of human history, we just used the fibers that nature happened to give us. But now, by understanding this blueprint, we're becoming architects at the molecular level. So the real question isn't just about what makes a fiber strong anymore, it's about what new worlds we'll choose to build with them next.